Hello, and welcome to this video where we're going to talk about proton NMR, just an overview of the key information obtained, and then in some follow-up videos, I'll break down the information obtained into their own separate videos. Okay, so the key information obtained in a proton NMR include the number of unique sets of hydrogens, the relative number of hydrogens for each signal, the number of adjacent protons, we get that from the splitting pattern, and then the neighboring chemical shift or chemical or electronic environment. That's where we look at chemical shifts. And then this is helpful for structural elucidation. And so I'll just demonstrate using info obtained from the spectra to help us do that. So these are the four pieces of information one gets from a proton NMR. The first one, how many non-equivalent hydrogens are in the structure. This will correlate to the number of signals that you're seeing in the spectrum, not the splitting patterns, but each individual signal that we're integrating. The integral, like in calculus, is just the area under a curve. And so the integral in an NMR is relative then to the number of protons in each set, giving rise to that signal. Okay. Exchangeable protons may not show up in a proton NMR. So if you have a protic proton, so if it's connected to an OH and NH, these often will exchange with solvents that are able to exchange deuterium. And so deuterium does not show up in a proton NMR, so it could be misleading sometimes. But dry organic solvents are usually free of exchangeable protons, and so they allow then all the peaks to show up. The multiplicity, this is the splitting pattern. And this will tell you about the number of protons on adjacent or vicinal carbons, nitrogens, and oxygens, or even on the same carbon, geminal, if they are non-equivalent. Chemical shift, this is the resonant frequency of the nucleus relative to the standard in a magnetic field. And so this is going to be influenced by the number of other hydrogen groups attached, or influenced by the electron or the electronic environment of the neighboring functional groups. And so what I mean by that is the electron withdrawing or electron donating effect of those adjacent groups nearby. And then lastly, there's a ring current effect. And this gives rise to induced magnetic fields. So this is the reason why aromatic hydrogens are so far to the left in the NMR field, or in the NMR table, or the NMR spectrum. So we'll look at some of the effects there as well. These four pieces of information will all be broken up into their own separate video, just to keep the videos shorter for you to watch. So this one is just overviewing what I've done, what I've done here, the information you're getting from the NMR spectrum. So here is an example of an NMR spectra. We have the molecular formula C11H14O2. So this can be very helpful when you're trying to determine the structure, if you already know the degrees of unsaturation. And so that will tell you how many pi bonds or how many rings or a combination of those that you better have in your structure. And so I like to call this SODAR. And so that's sum of double bonds and or rings. So I call that SODAR. And that's just the degrees of unsaturation. So for this formula, 2 times the number of carbons would be 22, plus 2 is 24, minus the number of hydrogens here. So 24 minus 14 is 10, divided by 2. So 10 divided by 2 equals 5. And so that means I've got 5 rings or 5 pi bonds, or a combination of pi bonds and rings that equal 5. But there's a big clue in this NMR as to what a lot of those are going to be resulting from. I've got aromatic hydrogens here around 7. So if I had a benzene ring, let's say, let's just say there was a group on there, and maybe there was another group somewhere else, I would have maybe say hydrogens showing up in that. And so these are the hydrogens we would see in the aromatic region, the ones on the ring. And so that tells me that SODAR of 4 is accounted for by just the benzene ring. And then I probably have some sort of a carbonyl or double bond somewhere else. So how many non-equivalent sets of hydrogens need to be in this structure? Okay, so that's what I wanted to focus on here. So you see, I have 1, 2, 3, 4, 5, 6. I have 6 signals. That means the structure has 6 unique sets of hydrogens in it, okay? Now the integral isn't being given here, but the integral would be the number of hydrogens that give rise to each signal that you see, okay? Without a structure, that's sometimes hard. So you have to kind of derive the integral from thinking about multiplicity, or you have to know what the structure is, so that way you can integrate individually. So what I will say is that if I integrate this to 1 and B has the same number of hydrogens, it's also going to be set to 1. So it's a relative number of hydrogens in that structure. So when you're integrating a NMR structure, you usually find a peak where you know the integral, set it to the number of hydrogens giving rise to that signal, and then all the other peaks will integrate relative to that, so that usually the integral equals the number of total hydrogens, unless there's symmetry. So right now I'll just say integral, that's the number of hydrogens in each set, and then total number should match the molecular formula. So I have 14 hydrogens in the structure. So the integrals here would all have to add up to 14 somehow. So the multiplicity, this tells you about the number of adjacent H's. And so we're going to use the N+1 rule for simple systems. When you start getting stereocenters involved, then the N+ rule becomes a little bit more complex. So what I mean by N equals the number of adjacent H's. So if I look at peak A, this is a singlet. And so N+1 equals 1. And so N is equal to 0. That means whatever set of hydrogens is giving rise to that peak, it's on an atom whose atom adjacent to it doesn't have any hydrogens attached to it at all. Okay, so the same thing I could say here, that's a singlet. And so N is equal to 0 as well. If you go to C, that's a triplet. So N+1 equals 3 because the triplet corresponds to the number 3. And so N would equal 2. So there's 2 neighboring hydrogens next to the carbon or atom attached to those hydrogens. Same thing down here. Here's a triplet. So N+1 would equal 3. So N is equal to 2. And at D, I have a doublet. And so N+1 equals 2. And that means N is equal to 1. Same thing for E, I have a doublet. So N+1 equals 2, and that means N is equal to 1 as well. And so That probably means there's some sort of symmetry in the aromatic ring to only give 2 signals. The reason I know this, if it were, say, benzene, I would have 1 signal. If it was a benzene ring, let's say it had 5 hydrogens attached, and then some non-hydrogen group, I'll just call X, then the unique number of hydrogens, I would have 1. Actually, I'm going to 1. I would have 2. And I would have, so I would see 3 signals, not 2. So the substitution pattern on the ring is important, and you can kind of get a sense for that when you look how many signals you're seeing in the aromatic region alone. So I'm going to erase this. I just wanted to show that as sort of a baseline example. So whatever ring I have here, since I only have 2 sets of hydrogens, I probably have a setup like this, where X is not equal to Y, or let's see if I could do another possibility. Maybe you have something like this, where X and Y are the same. Both of those would give 2 signals in the aromatic region as a result. Okay, so you can get a lot of information about connectivity by understanding and looking at an NMR spectra. Lastly, the chemical shift tells me about the electron withdrawing or donating environment. And so down here, it's more electron withdrawing environment than whatever else is attached to the far right of the structure. So you can see that in the different chemical shifts. So here is the IR for that compound, just to kind of help as well. And what you can see here in the IR, so this is where IR and NMR can kind of help each other out. You've got some CH stretches here. That we see, and you have 2 different types. Those corresponding to an sp2 hybridized carbon, maybe of an alkene. That makes sense because we've got double bonds in the ring that are attached to hydrogens. And then also here at about, I don't know, 1730 to 1750 or so, we have a stretch. So that's your carbonyl stretch, zone 4. Or these are all zone 2. So that gives me a little bit more information that I didn't have before. So I know SODAR is equal to 4 or 5, and we've decided we have a ring. So that knocks out 4 of the SODARs needed. And then I have a carbonyl, and so that knocks out the other SODAR. So again, you can get information from other pieces of spectra as well. And so I'll just leave this as a challenge to you. I'm not going to go through this right now, but can you draw the structure responsible for the IR and the proton NMR spectra shown? I will come back to this problem once I've finished talking about the other pieces of information individually. And so I'll follow up with going through this problem once again. So that ends this video, and thank you for watching.